right? In absolute value. And I needed the non-negativity here. And obviously I need non-negativity in this statement, because if I didn't have non-negativity, is it possible that dn diverges but an converges? Yeah, especially if the dn's are really negative and you're adding a bunch of negative things and they're going off to minus infinity, right? Okay, very good. Use a to show. And that's the contrapositive. Okay, excellent. Comparison test. All right. So now that we have the comparison test, a good thing to ask yourself is, what should we start comparing things to? What to compare to? Well, the first basic sequence to compare to is the geometric series, yes. Okay. Geometric series. So here's a theorem. Geometric series. This geometric series appears in the theorem. If the absolute value of x is less than 1, then, in fact, this sum, n goes from 1 to infinity, is 1 over 1 minus x. There. This is the sum formula that we've learned since maybe grade school. Actually, I don't know when you learned this. High school? Is it high school? Okay. Analysis. Okay, what can I say if x is bigger than 1 and equal to 1? Yes, the series diverges. Again, I'm stopping writing this whenever it's the indices when it's obvious. But this is something we also want to know. So it only converges if and only if the absolute value of the ratio that appears in the geometric series is, in fact, less than 1. Okay, how am I going to show this? How are we going to show this? Now, of course, it wouldn't, we're going to try to use comparison to compare lots of things to the geometric series. How are we going to show the geometric series converges when x is less than 1? Help? One plus x squared plus x. Well, to show something converges directly, you should go back to the partial sums. What are the partial sums? Here we go. I'm going to assume for the minute x is not 1. Then I'm going to let Sn be 1 plus x plus ... through x sub n. Okay? Now, this is a finite sum. So you really can't stop me from multiplying this by x minus 1, or 1 minus x, and seeing that you actually just get 1 minus x to the n when you do it. So Sn actually is clearly, you just factor, if you like, 1 minus x to the n plus 1, and you can factor out a 1 minus x. Okay, so this is just polynomial arithmetic. Usual polynomial arithmetic. You can see why that's true. Help. Now what? This is a partial sums. Yeah, take the limit. Very good. So the limit of the SNs is, well, it's the limit of 1 over 1 minus x, which has no dependence on n, times, so this is the limit of a product, is a product of the limits, times the limit of 1 minus x to the n plus 1 as n goes to infinity. Yes? Help? Well, this is what? let's just assume from the beginning x is strictly less than 1. Help. What can we say here? Yeah, it goes to 0. Sorry, 1 minus 0. Yeah, so this thing goes to 1 minus 0, so we get 1 over 1 minus x. Done. Notice that this is true if x is less than 1. That's where we've used it. Okay? So if x is less than 1, we have this as the limit. Now, if x equals 1 or minus 1, what can we say? Or, in fact, how about just take care of the whole case? X bigger than or equal to 1. Why do we know this thing diverges? A little easier. Terms don't go to 0. Right? Terms do not go to 0. So the sequence diverges. The series, sum of the xn, diverges. Excellent. Excellent. Any questions about this? In one fell swoop, we've actually just eliminated many of the major theorems about series, right? And we care a lot about series because, well, let's see, there's lots of examples from calculus, right? If you're doing limits of Riemann sums, that's the sum of a bunch of little areas of blocks, right? If you're constructing wave functions, waveforms from a bunch of sines and cosines, you're adding up infinitely many of them, you have to worry if the sums at any given point actually converge. That's a series. Okay, great. So what else? Let's take a couple-minute break, and after the break, I want to show you a few more series that we can say something about. We have to be a little more clever, though. Okay?